Okay, so like our sun, most stars have absorption spectra. And the reason for that is most stars have a photosphere that has gas. They're just not hot enough to make everything in the photosphere plasma. And also most stars have an atmosphere as well that also blocks some light. So except for the very, very, very hottest stars and most dense, almost all stars out there, we're talking like 99.99% of them have absorption spectra. They are not continuous. There will be some wavelengths of light that are missing. Now, as you can see with our sun, it is definitely absorption spectra. There are wavelengths of light that are missing, as I showed you earlier, and they're missing because certain elements of gas, so gas elements, are absorbing wavelengths because, well, light hits them and those electrons are being moved out and taking up the light. Oh, one other reason that we use spectral lines is this picture right here, taken by the Hubble Space Telescope. It shows two bright objects in the center here. One of these is a star. The other is in a galaxy 6 billion light years away. If you're just taking pictures, you would not be able to tell which is which. Now, obviously, that one's a galaxy, but these two look exactly the same without actually breaking them apart. But using spectra, we can tell, hey, wait a second, one of these is very, very redshifted and is moving away. So it must be far away from us, while the other is inside our own Milky Way galaxy and is probably not going to be really shifted at all. Not going to be shifted if at all. So we can actually use spectral lines to figure out distance, as well as all the things that you were mentioned earlier, like temperature, class of star, what elements are in it as well. So there's another thing that you can add to the list of why we use spectral lines. So for stellar spectra, like I mentioned, almost all spectra out there are going to be absorption spectra, and they tell you what gases are in the photosphere of that star, what gases in their atmosphere, and even what nebulas are between you and the star. So if there's a cloud of gas and dust between you and what you're looking at, absorption lines can tell you the difference. Now, one more thing that spectral lines can tell us is how much the universe or how fast the universe is expanding. And we're going to go more on that in our next module, but I just want to know we actually use spectral lines to figure that out as well. These things are really, really useful for astronomy. So now we're going to get into spectral classes. When it comes to spectral classes, we're talking about stars. And for stars, these lines are actually how we determine the temperature of the star. We can't take a thermometer and go to a star and put the thermometer in the star and say, yep, this star is 10,000 Kelvin on its surface. We can't do that. First of all, the stars are too far away. Second of all, 10,000 Kelvin would vaporize any thermometer you try and put in there. So we use these lines to actually figure out the temperature and use these lines to figure out the class of the star. I'll talk more about assignment 4.7 once we're done with this. So let's take a look at some spectral classes lines. Here's an M class star. K class isn't much different than M. And what you'll notice that with an M class star, if you just look at the picture really fast, is there are a whole bunch of lines. There is a whole bunch of light that is being absorbed from the M class star before it ever reaches their spectroscope. So what's going on there? Well, M class stars, they're red dwarfs. They're really, really cold on their photosphere. It's about 3,000 Kelvin for the cooler ones. So they're not really hot. And because of that, there's a lot of elements that are going to be absorbing light. There's going to be a lot of elements that are gases, and gases can absorb light. So you have titanium oxide. That's not even an element. That's a compound that's absorbing light. Sodium, it's going to be absorbing light. Calcium, and a whole bunch of everything in between. It's not just those three. There's a bunch of elements that are going to be a gas at 3,000 Kelvin. And so what you'll notice is that M and K class stars, the way to tell them whether you have like a red dwarf or a cool star is there's going to be a lot of lines. Easy way to tell. But let's get a little bit hotter. Let's move up from N and K. Let's get to A, F, and G, which includes our own sun at G class. Now you'll notice the difference between G class and M and K. If I could back it up a second, look at this, and then look at this. There's lines, but there's a lot less of them, and they're a lot less dark than the previous star. So for example, if we go to this, we go to the sodium line right here, notice that as you get higher up, the sodium line goes away and then it's gone completely by the time you get to A class star. So the hotter you get, the less lines there are. Once you get to like B class stars, 10,000 Kelvin, even these hydrogen lines start to get dimmer and dimmer and they start going away. And once you get to O, we're talking 30,000 Kelvin here for O class star. It's basically a continuous spectrum. Yes, there's a little bit of hydrogen lines, but you have the entire rainbow because O class stars are just so hot that their entire photosphere is covered in plasma, not gas. Plasma. And plasma does not block light. Gas does. but you can't have a gas at these high temperatures. So basically, this is the most important part right here. It says the hotter a star is, the less lines there are. Underline it, bold it, point some arrows at it. That is the key piece of information, the key takeaway from me showing you these pictures, is the more heat you have, the less gas you'll have and the more plasma. And since plasma can't block light, the less gas you have, the less light will be blocked, the less absorption lines you're actually going to have in this absorption spectra. So you start out with lots of lines because it's not really hot, less lines as it gets hotter and you have more plasma, all the way up to basically no lines because it's all plasma and no gas. And here's the spectral classification system in order so you can see. I'm really only going to care about the letters, O being the hottest, M being the coldest. If you want to write those down and point like an arrow pointing towards O saying higher temperature. If you want to do another arrow pointing this way saying colder temperature, I would recommend that. Could be good for your notes. Spectral classes here, I think we covered that. The spectral class tells you how strong the hydrogen lines are. Yep, so for these M class, you're not going to really have hydrogen lines because you got a whole bunch of lines, too many of them. Once you get into G and A, yep, there'll definitely be hydrogen lines there and there. And once you start getting hotter into like the Bs, the hydrogen lines will start going away because the star gets really, really hot. I don't think we need to cover that, but let's talk about a graph. So when we actually say absorption spectra, it's not a person standing out in a field looking at the stars with a telescope. It's a machine that's registering the intensity of light being received. So obviously purple light is going to be higher intensity because it has higher energy, while red light will be lower energy, and so it'll have lower intensity. But here's the thing, when this device is measuring the wavelengths, if there's, let's say, for example, hydrogen lines being absorbed, notice that a lot less light is being received by the detector at these 3 wavelengths. And so what that would look like when you graph it on a spectrum is, look, there is a part that is darker because, well, less light is being received at those wavelengths. It's going to be darker because light is light and light is bright. So this one red, this one blue, this one purple are missing. You can notice the dip in the amount of light received, the intensity. So this would probably be either an A or a B class star probably. And here's how you can tell. Look at all these stars, all the stellar classifications of stars right here, O, B, A, F, G, K, and M. Notice for O, yeah, there's a few dips, but basically O is just a perfectly straight curve going up towards UV as you get higher energy. And yeah, there might be some absorption spectra, but it's not making that big of a deal. B and A, they're almost perfect curves up, but notice that hydrogen, H, 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 there is some more dips once you start getting down into A, and those dips correspond to wavelengths of light being absorbed by gas. Once you start getting into F and G, yeah, there's a lot more dips. A lot of things are now being absorbed, especially for G. There's one there was one there, there, definitely one there, and then it drops down once you get into the UV. And then we get to our red dwarf, red and orange dwarfs down here, K and M. Look at this, M, yeah, basically no light, maybe a little bit, but only shines bright in red and infrared. And that's why we call them red dwarfs, right? Is because they have mostly red light. The rest is being absorbed or just not being emitted at all. So you can tell what kind of star it is based on the spectral lines, based on how much is being absorbed. And because of that, you can tell its temperature as well. Surface temperature, I should say. Okay, last thing we're going to learn about spectral lines that they're used for is redshift, blue shift. So if this was an actual star that was measured, we looked at its wavelength and saw these absorption lines, and this is what we would expect for that temperature of star, you'll notice that what we expect does not match up perfectly with what's missing. So what's happened here is all of these lines have shifted to the left towards the red. We call this red shift, and this would be for a star that is moving away from us. We'll talk more about this later. Notice that in this next one, the lines have moved from here to here. They've moved to the right. They've blue shifted. So they're not where they're expected to be. They're a little bit more towards blue for each of these lines. And we call that blue shift when an object is moving towards you, its light will be shifted more towards blue, crunched together, shorter wavelength. That's all we're going to talk about for now, but just know that this